Can you hear me? Hello, can you hear me?
Yes, sir.
Okay. So in this lecture, we will be talking about dimensionality reduction with PCA. Okay. And in the next class, we will be talking about linear discriminant analysis. So I have prepared this presentation from the book Pattern Classification by Ruda Hart. So you can find most of the contents in this book. Now, why we are interested in dimensionality reduction? So that we need to understand. Okay. Now let us consider we with respect to dimensionality. Okay. So in that case, we can represent the dimensionality along x-axis and performance along y-axis. Now, when we gradually increase the dimensionality of the data set, then we can see that after achieving the optimal point of performance, the performance getting decreases. Okay. So here the performance getting decreases, having the dimensionality increased. Okay. So if we increase the number of features, so that will not help us to improve the classification accuracy. Okay. So if I pick this point as an optimal point of performance, then we can see that after having the dimensionality to be increased along x-axis, so we cannot get the performance increased. Okay. So having the dimensionality increase, the performance is also getting gradually decreases. So this does not mean that having the dimensionality increase, the performance will also increase. Okay. So in practice, what we do in practice, the inclusion of more features might actually lead to worse performance. Okay. So having this idea to increase the dimensionality will also increase the performance will not work. Okay. So we cannot increase the number of features, so that will not always improve the classification accuracy or prediction accuracy. Now the number of training examples which are required increases exponentially with dimensionality D. Now here if I assume that K is a number of bins per feature, then we can see that here K equals to 3. Okay. So if I assume that K equals to 3, then there will be 3 bins per feature. And here we will get 3 to the power 2 number of bins for x1 for two-dimensional data x1 and x2. Okay. So therefore the number of training examples which are required increases exponentially with dimensionality D. So if I increase the dimension D for each data point, then we cannot get the performance to be increased. So for three-dimensional also, here you can see that the number of bins to be increased 3 to the power 3 when we have three-dimensional data. Now what is the objective of dimensionality reduction? Now we can choose an optimum set of features of lower dimensionality in order to improve the classification accuracy. Now we have to understand the we have to understand what is the optimum set of features. So with this performance graph, we can see if the optimum, if we exceed the optimum set of features, so that will not help us to increase the performance. Okay. So in this case, we can select this point as the optimum, this point as the optimal point for performance. After having the dimensionality increased, and then this will not help us to give us the optimal performance. Uh, in this case, the performance will be getting decreased. Now we can use the different method to reduce the dimensionality. So we can have two different choices. One is the feature extraction, another is feature selection. Okay. Now in feature extraction, we find a set of new features that is having a mapping function on the existing features. That means here in feature extraction, we try to find a new set of features having the mapping function on the existing features. Now let us consider here capital X is the existing feature set. Okay. So here x1 to xn is the number of samples and each xi is a vector. Now we can apply this mapping function on this existing feature set to get the reduced feature set. Okay. So if I denote the reduced feature set by y, then y1 to yk. So we here we can get the k dimensional data. So the here the k is found to be very less than n. Okay, and here the mapping function is f. So when we apply this mapping function on the existing data set x, then we can obtain a reduced data set y with k dimension. Okay, where k is found to be very less than n. Now the mapping function could be linear or non-linear. Now we have other choice of feature selection. So in feature selection, we choose a subset of original features. Okay. So in feature extraction, we find a new set of features having the mapping function applied on the existing features. But in feature selection, we choose a subset of original features. Okay. So here if we consider here x is the given data set of n number of samples or n dimensions, then we can have the reduced set of original features of k dimension where k is found to be very less than n. So basically feature extraction we find a new set of features, but in feature extraction we find a new set of features. In feature selection we choose a subset of original features. So we choose a subset of original features after discarding the irrelevant features or the features which are not important to the feature set. Now in feature extraction, we consider the linear combinations, linear combinations, linear combinations of features because they are simpler to compute and analytically tractable. Okay, so here we basically consider the linear combination of features in order to in order to compute. In order to make the computation simple and analytically tractable. Now suppose a feature set capital X is given to us which belongs to the feature space Rn. Okay, so here Rn is the feature space of n dimensional vectors. So here X capital X is containing n dimensional feature vectors. Okay, so dimension of each feature vector is n. So we have to find k by n matrix of T such that we can we can have y equals to t of x. Okay, we can have y equals to t of x that belongs to r to the power k feature space. So here basically here we try to reduce the dimension of the feature space Rn to the dimension of the feature space Rk. Okay, where k is found to be very less than n. So here we are doing a projection from n dimensional space to k dimensional space. So basically this T is found to be a matrix of k by n dimension. So where we project the n dimensional feature space onto a k dimensional feature space. Now from a mathematical point of view, finding an optimum mapping y equals to f of x is equivalent to optimizing an objective criterion. Okay, so we know how to optimize a loss function, so that we have already discussed. So here we are making the same assumption that finding an optimum mapping y equals to fx is found to be equivalent to optimizing an objective criterion. Okay, so so what are the different methods that we can use for getting the optimizing optimizing result or optimized performance? So we can use the different method. So we can use the minimize information loss. So what is minimize information loss? So this minimize information loss basically represent the data uh, in lower dimensional space. Okay, and maximize discriminatory information, it enhances the class discriminatory information in the lower dimensional space. Okay, so in this two different way we can optimize a function and find an optimum mapping. Now what are the different popular linear feature extraction methods that are available in machine learning? So there are two different types of feature extraction method or data reduction techniques. One is the principal component analysis, another is linear discriminant analysis. So in principal component analysis, uh, we seek a projection that preserves as much as information in the data as possible. Okay, and in linear discriminant analysis, we seek a projection that best discriminate the data. Now we can have other methods also, the independent component analysis. Then we can have the projection, so that will retain the interesting directions. Okay, we can have the embedding method, so that will have the lower dimensional manifolds. Okay, like one such method is locally linear embedding. Now let us consider a vector capital X that belongs to Rn feature space. Okay. Now this can be represented by n components. So n components means here we are having n number of vectors. Okay. So here each xi is we can say n dimensional feature vector. Okay. Now we can assume a base vector v1 to vn. So these unit vectors represent in each dimension. Okay, and here xi can be obtained by projecting x along the direction of vi. That means what we are doing here, initially the data set capital X will be given to us, and this data set will contain n dimensional data. N dimensional data means each feature vector having n dimensional features or n dimensional attributes. Okay, now in another step we are considering the base vectors. Base vectors means here v1 to Vn. Okay, and we are trying to project the given data set X along the direction of Vi. Okay, so here V1 to Vn is the number of unit vectors, or we can say the base vectors. So therefore, we can compute xi, which is given by transpose of x multiplied by vi, and this will divided by uh, transpose of vi multiplied by vi. So what does this mean? So transpose of x, which is multiplied with vi, so this is nothing but the linear combination of each data point, linear combination of each data point with basis vector. Okay, and this is divided by the orthogonal basis of transpose of vi and multiplied by vi. So this will give us the transpose of x into vi. Okay, so basically for this denominator, so we have two different conditions. That means when both these unit vectors or the basis vectors are found to be same, then this will uh, found to be same, then this will give us 1. Okay, that means both these vectors represent the same, lie on the same line, or we can say the both these vectors will found to be the same line. Okay, and if these vectors are found to be orthogonal, okay, that means we can write we can have the linear combination of the transpose of vi, and vi will give us 0. Okay, so basically what we are doing, we have been given a data set capital X of rn dimension or n dimension, and we are considering another n-dimensional unit vectors. Now we are trying to project the given data set along the direction of unit vectors. Okay, now after projecting x along the direction of vi, so here x can be reconstructed from its projections. So after having the projection of the given data set, then we can reconstruct the x from the projection itself. Okay, and this reconstruction will give us the linear combination of xi and vi. Okay, linear combination of xi and vi. So therefore we can write capital X equals to summation over xi vi, where I varies from 1 to n. Okay, so basically when we reconstruct the x from the projections, we are taking the linear combination of xi and vi. So so since the basis vectors are the same for all x belongs to Rn feature space, or we can say other way we can say the standard basis. So we typically represent them as a n component vector. Okay, so that is why we are having this data set capital X. So here this data set is n component vector. Let us assume here n equals to 2. N equals to 2 means we are having two-dimensional data. Okay, that means we can write r to the power 2 feature space. So in this r to the power 2 feature space, we can have a number of feature vectors, and each feature vector having two-dimensional data. So here capital X we can write capital X having a number of feature vector, and each feature vector having two-dimensional features x1 and x2. Okay, now for x1 and x2 we can write we can assume 3 and 4, these two values. Okay, And when we plot this point in the xy coordinate, then we can have this point. Okay, so this arrow represent the direction of this point. Now we can also assume this x-axis as I and y-axis as j. Okay. Now we can also assume that the standard base vector v1 is I and v2 is j, and here xi can be obtained by projecting x along the direction of vi. Okay. Now we can assume any value for basis vector. So since we are having two-dimensional data, therefore the number of basis vectors will also be two-dimensional basis vector. Okay. So here we can see that if I consider the basis vector is 1 0, then we can compute x1 equals to transpose of x into I. So what is I here? I is a vector of 1 0. Okay, and here x is a vector of elements 3 and 4. So we can get the combination of this transpose of x and basis vector I. Okay, and this will give us the x1 equals to 3. Now we will compute for the basis vector j, that is v2. Okay, so similarly for x2, we can get the projection x2, which is given by transpose of x multiplied by j. Okay, so we know the x2 is 3 4. Okay, and for j we get 0 and 0 1. Okay, so this 0 1 will be combined, this 0 1 vector will be combined with the given vector x, given vector x, and this will give us the projected value of x2 as 4. So first we get the projected value for x1, then we get the projected value for x2. Okay, so this is the way to project a given data set along the direction of basis vectors. Now after having this projection, now we have to reconstruct the x from the projection. Okay, so for this we can have this function x equals to 3i plus 4j. Okay, so we can use this reconstruction function to obtain the reconstructed data from the from the projection that we have obtained for two-dimensional data x1 and x2. Now since we are talking about the principal component analysis, and before we get into the details of principal component analysis, so we needed to understand how how the projection works with basis vectors when a feature vector or the data set x is given. Okay, now the main objective of PCA is to identify the patterns, so that will reduce the dimension of the data set with minimal loss of information. Okay, so this is the main objective of the principal component analysis. Now what PCA does, PCA projects a feature space onto a smaller subspace. Okay, and that represent the data well. So initially, as I said earlier, as I said in the previous slides, that when we have been given a dataset X of n dimension, then we have to reduce the dimension of n to dimension of k, so that we can get the smaller subspace. So in PCA, basically we are interested to find the directions that will maximize the variance in the data set. Okay, and This means the data is found to be more spread within a class. Now, since we know about the principal component analysis, is that the principal component analysis is the unsupervised data reduction techniques. So initially when X is given to us, this X is found to be without having the class level or class information. Now the entire data set or entire data set belong to one class. Okay, if we say the entire data set is not having any class information or class level, then we can assume the entire data set belong to a single class. Okay. Now in PCA we are interested to find the directions. Okay, so direction means the components. So gradually we will learn these directions are nothing but the principal components. Okay, and when we find the principal components or the directions, so these directions maximize the variance in the data set. Okay, and in other way we can say that the data is found more spread within a class. So principal components will correspond to eigenvectors and eigenvalues are associated with eigenvectors. So this principal when we get the principal components, so these principal components will correspond to eigenvectors, and here we are interested to obtain the compute the eigenvectors and eigenvalues. Okay, and since the principal components correspond to eigenvectors, so therefore before we compute the eigenvectors we need to compute the eigenvalues, and these eigenvalues are found to be associated with the eigenvectors. Okay. Now, what these eigenvalues represent? So, eigenvalues represent the magnitude of represent the magnitude of the eigenvectors. Okay, so and these eigenvectors are nothing but the basis vector that we are interested to compute. So, when eigenvalues are found having similar magnitudes, so it is said to be good subspace. Okay, since we are interested to have the ideal case of good subspace or the smaller subspace that we are interested to obtain. So therefore in ideal case the eigenvalues, when the eigenvalues are found to be having smaller magnitudes, okay, then this can be said as the good subspace. Now suppose here X belongs to Rn, X belongs to Rn feature space, and then it can be written in a linear combination of an orthonormal set of n basis vectors. Okay, so orthonormal set of n basis vectors v1 to vn in the feature space Rn. Now if we consider, so you can assume there is a circle and this circle represent Rn feature space or n-dimensional feature space where we can have a number of feature vectors. Okay, and each feature vector, and this number of feature vector means this number of feature vector is represented by the capital X, the data set capital X. Okay, and each feature vector is having n dimension. Now when this data set can be written in a linear combination of orthonormal set of n basis vectors v1 to vn in Rn. So therefore we can have these two different conditions. Okay, so if I is found to be j, so therefore we can write transpose of vi transpose of vi and vj will give us 1. Okay, so that means the if here we can see that when there is when both this unit vectors or both these basis vectors are found to be on the same line, so there will be so that means there will be no that means this transpose of vi or vi is not making any orthogonal orthogonal basis with vj. Okay, that means they are not orthogonal to each other. So if they are found to be orthogonal to each other, then we can see that r I not equals to j. Okay, and in that case this transpose of vi and vj will give us 0. That means cos uh, uh, here we can have the cos 90. Okay, in the first case we get the cos 0, so this cos 0 degree will give us this one, and cos 90 degree, 90 degree means this vi and vj is orthogonal to each other. So if if we can consider this is vi and this is vj, okay, then we are getting 90 degree. So for 90 degree, or for this orthogonality of vi and vj, we get this we get this 0. Okay, and when they are found to be on the same line, on the same direction, then I will be found to be equal to j, and for that this will give us 1. Okay, so here x can be written as the linear combination of xi and vi. So when we reconstruct the x from the projection of the given data set along the basis vectors, then from that projection we can reconstruct the x as the linear combination of xi and vi. So we have already observed that how to compute each xi. So at this point, the PCA seeks to approximate X in a subspace of Rn using a new set of k dimension where k is found to be very less than n basis vectors. So here u1 to uk is the basis vectors, and they are also found in Rn. That means with these basis vectors, we can approximate the given dataset X in a subspace of Rn. Okay, so initially we are having Rn feature space. From this Rn feature space, we will obtain a smaller feature space, and that is referred by the approximation of X. Okay, that is referred by the approximation of S. So in that case, we will get a new feature set of k dimension where k is found to be very less than n. Okay, so in that case we can write this f cap, which is given by the summation of yi ui. Okay, so summation of yi ui. So this is nothing but the linear combination of yi and ui, where I varies from 1 to k. So the k represent the reduced dimension of the data. So, and where each yi, that means after having this linear combination from the projection, where each yi is given by this transpose of x ui, okay, divided by transpose of ui and multiplied by ui. Okay, so yi in other way we can write yi equals to transpose of x multiplied by ui. So here ui represent the basis vectors, and here x represent the given data set. So initially this will be given to us, and when we approximate the given data set x, so we will have this another data set of new features. Okay, so x cap is given by y1 to yk. So here k dimensional data set is obtained. So here we have to minimize the norm of x minus x cap. Okay, so this to be minimized. So this after minimization, so information loss will be very less. Okay. Now the optimal set of basis vectors u1 to uk can be found as follows. So in the first step, we will find the eigenvectors ui of the covariance matrix of the training data set, or training data sigma x. Okay. So initially what we will do, we will obtain the covariance. So from this covariance, we will find the eigenvectors or the basis vectors ui. Okay. And when we compute the eigenvectors or basis vectors ui from the given covariance matrix, then uh, we can write the sigma x ui equals to lambda I ui. Okay. So here sigma s represent the covariance matrix, ui represent the eigenvectors or the basis vector, and lambda I represent the eigenvalue. Okay, this lambda is the eigenvalue and this sigma x is the covariance matrix. So basically what we are doing, we are computing the eigenvectors ui from covariance matrix, so that we have to compute. And this the combination of the covariance matrix and basis vectors will be given by the eigenvalues lambda I, the combination of eigenvalues lambda I and basis vector ui. And in the second step, we will choose the k largest eigenvectors ui. Okay, and that will corresponding to k largest eigenvalues. So why we are interested to having the largest eigenvectors ui? So basically, as I said earlier, that here eigenvalues associated with these eigenvectors, and each eigenvalue represent the magnitude of the eigenvectors. Okay, so for the eigenvectors, for those eigenvectors, we are getting the magnitudes of the eigenvalues larger. So the corresponding eigenvectors will be selected, or the corresponding eigenvectors will be considered. Okay, for k largest eigenvalues lambda I. So this lambda I will be arranged in decreasing order, and the first few eigenvalues will represent the maximum variance. Okay, so maximum variance of the eigenvectors, that means the spread of the data for the first few eigenvectors are found to be maximum, okay, or higher. So therefore we are interested to select the first few eigenvector based on the largest eigenvalues lambda I. So here u1 to uk correspond to the optimal basis. Okay, u1 to uk correspond to the optimal basis, and we refer to the largest eigenvector ui as principal component. Okay, principal components. Or we can say the principal axis, or we also say the principal directions. Now let us consider we are given x1 to xm samples. Okay, so here each xi is having n number of features or n number of attributes. So therefore we can write x1 to xm. So here m is the number of samples and n is the number of features. In the first step, we will compute the sample mean. Okay, so sample mean is represented by this x bar. So this x bar is given by 1 upon m summation over xi. So for m number of samples, we compute this mean. In the second step, we subtract the sample mean. Okay, we subtract the sample mean. So that means the center data at 0. Okay, and this subtraction is represented subtracted value is represented by this phi I. So this phi I is given by xi minus. Basically, here we are computing the deviations from the centroid. Okay, so deviations of each xi from the centroid x bar. And in the third step, we compute the sample covariance matrix sigma x. Okay, so after having the mean and the deviations, now we are interested to compute the sample covariance matrix sigma x. Okay, and this can be computed as sigma x, which is given by 1 upon m for m number of data points. We are computing this covariance matrix, and this 1 upon m multiplied by summation over this xi minus x bar, then this is multiplied with the transpose of xi minus x bar. That means this summation is calculated over the deviations, which is multiplied with the transpose of deviations. Okay, so in other way we can write 1 upon m and this summation over phi I transpose of phi I. Okay, where I varies from 1 to m. So here you can see that 1 upon m a then transpose of a where a represent phi 1 to phi m. Okay, this phi 1 to phi m means the deviations, and the columns of a are the phi I. So the matrix will be dimension n by m. Okay, n by m. The next step, we compute the eigenvectors and eigenvalues and eigenvectors. So before we compute the eigenvectors, we need to compute the eigenvalues so that we can arrange the eigenvalues in decreasing order, and we will consider first few eigenvalues and the corresponding eigenvectors based on the magnitude. Okay, so for that we can write sigma x ui, okay, equals to lambda ui, and here we assume that lambda 1 found to be greater than lambda 2 found to be greater than lambda n. Okay, so this lambda 1 to lambda n represent the n number of eigenvalues for n dimensional data. Okay, so for n dimensional data, we will compute this n number of eigenvalues, and then we will arrange the n number of eigenvalues in decreasing order, and then we will consider first few eigenvalues and their corresponding eigenvectors. So here, since sigma x is a symmetric, uh, here sigma x is symmetric, so here u1 to un will form an orthogonal basis in Rn feature space. Okay, orthogonal basis in Rn feature space. So we can represent any x that belongs to Rn feature space as x minus x bar. Okay, x minus x bar. So this is given by the linear combination of yi ui. Okay, so in place of yi, what we can write? We can write transpose of x minus x bar multiplied by ui, the basis vector, divided by this denominator part. Okay, and this is given by transpose of x minus x bar multiplied by basis vector ui. So when the norm of ui is found to be 1, so norm of ui is found to be 1, that means when when the when the angle between two basis vectors are found to be 0 degree, then only we can write transpose of x minus x bar multiplied by ur. In that case, the denominator will be found to be 1. Otherwise, it will be found to be 0, and in that case, we cannot in that case we cannot compute the yi, so the value of the yi will be found to be infinite. Okay, now in the next step, so this step is very important. This step is known as the dimensionality reduction step. So in this step we approximate x using only the first k eigenvectors. Okay, first k eigenvectors. So we are not using all the n number of eigenvectors. We are only considering k number of eigenvectors, and using this k number of eigenvector we approximate the given data set X. Okay, and this k number of eigenvectors will correspond to k largest eigenvalues where k is a parameter. Okay, so we can write the same combination of linear combination of yi and ui, and then here we show the approximation of ax by x cap. Okay, so using the first k eigenvector we approximate the x. Okay, and this approximation is represented by x cap. So therefore we can write x cap minus x bar equals to this reconstruction. Okay, so reconstruction for k number of eigenvectors. So for k number of eigenvectors we can write this linear combination of yi and ui as a summation, and this summation will be computed over this linear combination yi ui where I varies from 1 to k. Here you can see that if you try to visualize this reconstruction as an approximation of x, then here you can see initially we will have n-dimensional data, then we get y-dimension, then we get n-dimensional data. This is the projection. Okay, and from this projection we get this reduced set of data set. Okay, reduced set of data set of k dimension. Now, if k is found to be n, then x cap will be found to be x. That means the approximation will also found to be same as the given data set x. That means here the construction error is found to be 0. Now, when the linear transformation y equals to tx is given, then this transformation will performs the dimensionality reduction in PCA. Okay, so the same derivation we can write over here for k number of eigenvectors, and here for k number of basis vectors or k number of eigenvectors we can write u. So this capital U represent the k number of eigenvectors. Okay, and this is nothing but the n by k matrix. So the columns of U are the first k eigenvectors of sigma x. So therefore this can be written as transpose of U. Okay, and combination of transpose of U and x cap minus x bar. Okay, so T of here T can be given by transpose of U, that is k by n matrix. Okay, k by n matrix, and the rows of T are the first k eigenvectors of. So here what we are doing, we just transpose the eigenvectors so that the rows of T are found to be the first k eigenvectors of covariance matrix sigma x. These are the extra calculations. So from these extra derivations, we are able to understand the form of sigma y. Okay. Now, what we can interpret from this computation of principal component analysis. So basically here PCA chooses the eigenvectors of the covariance matrix correspond to the largest eigenvalues that we have established in our calculation, and The eigenvalues correspond to the variance of the data along the eigenvector directions, and PCA projects the data along the directions where the data varies most. Okay, that means in not the any other direction, not a random direction will be selected. So we are interested to have the direction of the projection where the data is found to be vary most. Okay, that means the variance will be higher when the variance will be found to be maximum. So in that direction we are interested to project the given dataset X. So PCA preserves as much as information in the data by preserving as much as variance in the data. Okay, so here you can visualize. Let us consider, here we have computed two eigenvectors u1 and u2. These are the nothing but these are the basis vectors. Okay, and here u1 is the direction of the maximum variance, and u2 is making orthogonal to u1. That means this u1 and u2 are found to be orthogonal to each other, and in the direction of u1 we found the maximum variance of the given data set. Okay, so therefore we are interested to consider the eigenvectors u1 u2, so in this direction. If you have any questions you can ask me, otherwise we will stop now, and tomorrow we will have a class on problem solving session. Okay, so tomorrow
Sir,
we will. Yes,
can you send some sample problems?
sample problems in this PPT. There is one, there are two problems with solutions are given. Okay, so today I will upload this PPT on the Moodle platform, so you can get this PPT from there. And apart from that, tomorrow we will have a problem solving session. So in that problem solving session, we will be talking about some problems and their solutions, how to solve those problems. Okay.
The
Today I will
problems,
upload this.
sir, problems on the previous topics. I mean, sir, you have last, sir, discussed about the problems on, sir, decision trees, and sir, the topics study which were taught.
See, the thing is that we have already discussed one problem from decision tree. Okay. And tomorrow I am going to discuss few more problems from one problem from PCA, two problems from likelihood methods. Okay, one problem from base classifier.
Okay, sir.
So in this way you can get the idea of solving this type of problems from
Yes,
machine
sir.
learning. Okay,
Yes, sir.
okay. So that's all for today.